Good morning, AP Chemistry students. Thank you so much for joining us yet again on an awesome day of chemistry instruction. My name is Sean Byrne. I'm coming to you from outside Chicago. I am a teacher at Glenbard West High School, which is in Glen Ellen. Go Hilltoppers. I know that a lot of us are watching from Glen Ellen. Today is Tuesday, March 31st, 2020, and we have some really great lessons in store for you today. Before we get started, we're going to start just quick reminders, like we do most days, of where you should be going for all of your most up-to-date information about AP tests and all things College Board, apcentral.collegeboard.org. Click on the link there for some specifics on how we're supporting you and your school for coronavirus precautions. You'll see a site that looks something like this. And I'll just highlight a couple of really quick reminders in case this is your first video. Remember that our face-to-face exams will not take place this year. Everybody is taking a 45-minute free response exam on their own device. We'll have 2 different dates for that to happen, and lots more information will all be released to myself and Mr. Fairbaugh and the public on April 3rd. So we're all holding on to this April 3rd date and encourage you to keep checking back to apcentral.collegeboard.org for the most up-to-date information. We know that our exam is going to focus on units 1 through 7, and units 8 and 9 will not be directly tested on this year's AP exam. However, that is still important information for those of you that will be moving on to other chemistry or other science classes. So Mr. Fairbaugh and I are going to do a good job of sprinkling that content in throughout the rest of our time together. I did notice this morning that more and more of our topics have been populated into our YouTube playlist. So if you want to see what the upcoming topics are going to be, and notice that while we started at Unit 8, we've bounced back through Unit 1 and 2 moving forward, and this is continuing to be added. More information is being continued to added on the YouTube channel every day. So keep checking back there. All of these are still recorded, and we've noticed that a lot of you are going back to rewatch the best of videos from last week. So continue to do that. That's a great resource for you that are going to be here for the rest of this year, at least, as we prepare for our AP exam in the next couple months. Our lesson overview for today, we've got a lot of content to cover, so I'm going to get right to it. We're going to do a quick review of our homework problems from yesterday. Oh, not from Friday, from yesterday. And then we will be looking at 4 topics from Unit 1 of AP Chemistry. And then I'll give you some AP practice to look at for homework tonight that Mr. Fairbaugh will get review with you tomorrow. Just a quick reminder of 2 things. Anytime that you need to stop this video, work out a problem on your own, have a piece of paper right next to you or a notebook or something where you can collect all of your materials. Feel free to stop, rewind, take a minute to get your calculator out and see if you agree with the work that we're doing. A special note about today's lesson is that you're going to notice that I have grabbed a couple of images from a site that's OpenStax. This is an open source, freely available chemistry book that's available to any of you. If you have your chemistry book at home, if you left school your last day and you brought your chemistry book at home, then you should be relying on that, because that's the book that you've been using all year and that your teacher is presumably going to be teaching you lessons from. If you don't have a chemistry book at home, there's lots of open source chemistry books online if you do a search for it. This is a very good one that I have experience using, which is why I'm using it here, but this is not endorsed per se by the College Board or by AP or anything like that. There are multiple sources out there that are really good. So I just wanted to make sure that I was giving credit to a great source. You'll see the couple of slides where I've used it today. You can look for this one or others online wherever you need to. All right, so let's get to a review of our homework problem from yesterday, which is our warm-up for today. We looked back at some mass spectroscopy of a specific element of neon here. And in this case, it's a little bit of a switch of what we talked about yesterday. Instead of looking at a graph, we're told that the average atomic mass for neon starts at 20.18 AMU. And so we're also told there are two common isotopes of neon that are in the table over here. And so this is a good example of how the masses may be slightly different from the mass numbers that we were working with yesterday. But the problem is asking us to calculate the percent abundance of each of the isotopes that's here. And so what we're going to do is we're going to let X equal the percentage of neon 20, and we'll let Y equal the percentage of neon 22. And so our equation would look something like this, where 20.81, our average atomic mass, is equal to 19.99 times the average, times the percentage of neon 20, plus 21.99 times the average of, the percentage of neon 22. We also know that X plus Y has to equal 100%. Okay, we're told that there are only two common isotopes that we're looking at here. One of the sources of error, if we were looking at this problem with a more complicated atom, might be that there's 3 or 4 or 5 common isotopes. And we certainly could do one of those problems if we had more time, but we're going to keep it simple here with just 2 isotopes that have to add up to 100%. And so one trick that we'll use is the fact that we can rearrange this equation to say that Y is equal to 1 minus X and plug that in over here for our value for Y. So now we go from having 2 variables in an equation, which is pretty difficult to solve, to only having 1 variable in our equation. We have our X value. We can distribute our 21.99 here. We'll isolate our X, and we'll come up with X being equal to 0.91. Then we bring this X back over here, plug it into our Y to say that Y is equal to 0.09. 0.09 plus 0.91 is going to be equal to 1.0. And then we can go back and we can convert both of these into percentages again to say that our percent of neon 20, X, this is why it was really important to define what our variables were at the beginning, right? X is equal to our percent of neon 20, so that would be 91%, and Y is equal to our percent of neon 22, which would be 9% down here. And so there's our final answer for that kind of a problem. Okay, so this is 2 different ways. If you go back and review our lesson from yesterday, we were given our percentages and asked to find the average atomic mass. Here we're given the average atomic mass and asked to find the percentages. So if you put those 2 problems together as practice problems for yourself, you should be able to solve both kinds of problems. If you were paying attention yesterday, you may have noticed that I left a key piece of information out of our second practice problem, and I apologize for that. Thanks to Mr. Faribaugh for pointing that out for me halfway through the day yesterday. We needed to know, in order to solve this problem correctly, we needed to know that the entire sample of the problem of the compound was 31 grams. So if you got stuck in this one because you didn't have that information, I apologize. Now's a great time for you to pause and see if that key piece of information helps you to be able to solve the rest of this problem. If you're still with me, I'll go through the problem here and show you how I would solve it given that key piece of 31 grams. We could, without that, we can still start the problem by looking at how much carbon dioxide is produced as a result of this burning in oxygen. When we burn that, we have 44 grams of carbon dioxide that are produced. And so that tells us that we have 1 mole of carbon that was originally in the compound. The only place that the only source of carbon was our original compound, right? So all of the carbon that's in carbon dioxide had to come from here. So if we have 1 mole of carbon in the carbon dioxide, that means we had 1 mole of carbon in our original compound. And similarly, we can take the amount of water that we produced, convert that to moles, and then say that there were 2 moles of hydrogen. You see where that came from down over here, 2H2, 2 moles of hydrogen for every 1 mole of water, and that gave us 5 moles of hydrogen. So how are we going to figure out how much nitrogen is in our original compound? Well, this is where we can just do a little bit of quick math. We're going to say our original sample was 31 grams. We had 1 mole of carbon, which would have a mass of 12 grams. We have 5 moles of hydrogen because each of them is 1 gram per mole. We can say that we had 5 grams of hydrogen. And when we subtract both of these out, that leaves 14 grams of nitrogen, right? So this is the key piece of information that we were missing yesterday. And this gets us to how many grams of nitrogen were originally. If it was only elements of carbon, hydrogen, nitrogen, we know how much the original sample was. We take out the carbon and the hydrogen, so whatever is left is nitrogen, okay? So we go through the similar process. We had 14 grams of nitrogen times 1 mole of nitrogen. This is the molar mass, gives us 1 mole of nitrogen there. And so our empirical formula, this is, remember, the lowest ratio of elements to one another, is CH5N, okay? 1 mole of carbon to 5 moles of nitrogen to 1 mole of, 5 moles of hydrogen and 1 mole of nitrogen. So in order to get to the molecular formula, we would have to do some other kind of experiment. We'd have to have some more information, and that's beyond what would fit into this this problem as it's written in this topic as we discussed it yesterday, okay? The last problem is from the 2018 chemistry free response question exactly. We're given a particle picture and you were asked to draw your own version of a particle picture that describes what the reactant mixture would have looked like. In the box on the left, show the reactant mixture of NO and O2. So one key piece of information when you're solving this problem is either to look at this or to go back to your original equation, okay? So the only things that should appear in your reactant mixture are NO and O2. The second key piece of information is to remember that the conservation of particles here, the concentration of mass, is that all of these particles that are represented here must be represented over here. They can be rearranged, and in fact, a chemical reaction, of course, rearranges the particles, but however many particles we ended up with, we have to have the same number to begin with. So for me, what I did is just organized how many of each atom we had, and I just made 2 columns of them here. I have 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 nitrogen atoms over here, and I counted up the number of oxygen atoms and listed them all right in here. Okay, and then I went back to my original equation. So here's conservation of matter, right? However many particles were here, I had to have from the reactant. They came from somewhere. They had to come from over here. The second part of it is that the only arrangement of the atoms is either in NOs or O2. So because oxygen could be in either of these places, but every nitrogen must be connected to an oxygen. I just kind of zipped them all together like this to say that every nitrogen, all of these NOs are over here, and then the oxygens are going to appear in the gaseous form as the diatomic molecules that they are, NO. And so the scoring guidelines tell us that there's 2 points for this, one for having the same number of particles on either side, and the second part for having them arranged in the proper way as we have it right here, all either in NO or in O2. Okay, so this would be a great one to take a screenshot in. Depending on how I drawn this picture, I probably would mix them up. I wouldn't put them in these nice little stacks like this. If you see the scoring guidelines on AP Central, you'll see that they're mixed up a little bit, but you would see something similar to this, at least in terms of the quantity and the arrangement of the particles. All right, so similar to what we did yesterday, we're going to mix together the what you need to know and the guided practice. We have a lot of content to get through today, so I'm going to be speeding through a number of different complex topics. So I'm going to just encourage you to use that pause button anytime you need to in order to reread or re-listen to some of my explanations, look back at the pictures that we've provided for you, and listen to it as many times as you need before you get to that guided practice. We're looking at these 4 topics, the last 4 in Unit 1 about atomic structure and electron configurations. We'll look at photon electron spectroscopy. So this is a little bit different than what we looked at yesterday. Similar, but here we're going to be focusing on electrons. Seriously, one of my favorite topics in all of AP Chemistry is periodic trends, and I could spend all day talking about that today if you wanted to, but I promise not to. And valence electrons and ionic compounds, which are related through all of this. What you're going to notice as a theme through all four of these is the way that electrons are behaving in all of these topics, or how electrons are behaving in atoms in general, and how that has an effect on how compounds and atoms will behave when they're interacting with one another. So try to keep that idea in the back of your brain. We're looking at electron configurations in this first topic, and we're going to use this idea of the Aufbau principle to, and we'll introduce Hund's rule as well in order to be able to draw and explain what's happening in electron configurations. It's important for us to remember that this is just a model, right, of what is happening inside of an atom, and that atoms are far too small and particles are moving the subatomic particles are moving way too fast to have a specific snapshot of what's happening here. But all of these models that we're looking at help us to understand more organization of the atoms, more organization of how the electrons will behave. And so any of the pictures that are up here, we know are just models of how atoms interact with one another. So important information for us to know, starting way at the beginning here, that we know that atoms have negatively charged electrons on the outside and a positively charged nucleus. You can go back and study your scientists who contributed to this understanding and some of the really amazing experiments that they had throughout much of history. One of the important things that's highlighted in this topic is Coulomb's law, which is a shout out to our physics friends that are listening as well, where we're going to calculate the force between two charged particles. And that force is proportional to the product of the two charges, the two charged particles, and inversely proportional to the square of the radius between them. So this is a good example of an inverse square relationship, where the further away something is, the more drastically this force is going to disperse or would lessen. There are multiple examples of this all over nature, and so it's cool for us to be able to talk about this here, because forces is something that's so integral to what happens in physics. This is a connection to other courses that you'll see. We're going to keep our relationships pretty qualitative in our discussions today and in a lot of the problems that I've looked at, but just being familiar with this idea that the force will decrease as particles get further away from each other is something that is pretty intuitive to most of us, I think, but keep that in the forefront of your brain as you're working through today's problems. In atoms and even in ions, electrons are organized or thought of as being in shells and in subshells. Again, this is just a model, but it's a very useful model for us as we're looking through our lesson today. Electron configurations will describe this model. We'll put this model in order such that we can see core electrons. What we call core electrons are the ones on the inside, and then valence electrons, which is a phrase I hope that you are familiar with, are the outer electrons, are the ones that are on the very outside of our atoms. And so we look at a picture like this that's going to help us to organize our electron configurations. And what we're going to see here are subshells that are listed. We have S's, we have P's, we have D's, and we have F's. Each of these lines here represents a subshell that is capable of holding electrons. And when we're given a problem like argon, which has 18 electrons in it, what we're going to use is a principle called the Aufbau principle. I've read multiple times that Aufbau in German means to build up. I've even talked to the German teacher at our school, and she confirms that that's one translation of that word. And so what we're going to see is that electrons are added to the lowest subshells first. So that's what's so great about a picture like this or a diagram like this. You're not going to be asked to recreate this as such, but it's a great picture to have in your brain as you are adding in electrons, or as we're trying to go from a example of argon has 18 electrons. What does its electron configuration look like? You may want to think about how you would fill up this chart from the bottom to the top in order to get to the electron configuration. And so as I add electrons, each of these arrows would represent one electron. So that we start at the bottom. We know that we typically put the arrows in opposite directions to indicate their spin. So one up and one down for the 1s, there's 2 electrons there. 2 more in 2s, so we're at 4 electrons. So I'm building up and I'm kind of counting to get to this 18 electrons in argon. There's 6 more that can be in the 2p orbital. Now we're at 12, 13, 14, 15, 16, 17, 18 electrons there. So we have 18 total electrons that are now accounted for. Now we've organized them in this diagram to help us to get to our electron configuration. And so from here, we should be able to write an electron configuration as 1s2, 2s2, 2p6, 3s2, and 3p6. So what I'm listing is the principal energy level. We know that the principal energy level number 1 has 1 sublevel, 2 has 2 sublevels, 3 actually has a third one possible, but we don't have enough electrons to get there yet. We'll see 1 in just a minute. And 4 has 4, 5, 6, the 4th principal energy level has 4 orbitals right here. So this is obviously a very complicated process. The way that electrons behave in a atom is super complicated. What this picture is doing is helping us to understand how we use the Aufbau principle to build up the electrons and get to a electron configuration that looks like this. A second way that we could represent an electron configuration is using something we call the noble gas configuration. And that's where we look at the bracketed electron configuration here as the noble gas that appears directly before argon. We typically probably wouldn't do this for a noble gas itself, but if I looked at the bracketed electron configuration here, I could replace that with neon and then add on whatever electrons are after that, that noble gas. So these 2 different electron configurations, this one and this one, both mean the same thing, and they're both an accurate representation of the electron configuration for argon. Okay, let's take a second. You could stop here and look at vanadium. Vanadium is another element that has 23 electrons in it. If you wanted to try to use that Aufbau principle and to fill up our electrons from the bottom to the top to build up electrons, you could do that in a picture like this. Either do it in your brain or just sketch something out on your piece of paper. And those of you that were paying really close attention in our last problem, notice that we were using a second rule that guides our electron configuration creation, and that's called Hund's rule. And that tells us that each sublevel should have 1 electron before any are doubled up. That's each sublevel within a principal energy level. So that's going to be looking at anytime we have 3 in a row right here, 3 in a row, or 4 right up here. Okay, so you may have noticed that for 1s, we have 2 electrons there. For 2s, we have 2 electrons there. Okay, but for 2p, when I was filling these up, I spread them out, right? I put 3 pointed in the up direction before I filled in a 4th that was going down. And that's an example of Hund's rule. We would not necessarily notice that for something like vanadium because the 2p sublevel is completely filled up, the subshell is filled up. The same thing would be true for 3s, 3p, we're going to see that we put 1 in each of those before we double any of them up. 4s, we'll talk about that in just a minute, has 2 electrons, but then our 3ds will get spread out. And so what we can talk about is that each of the electrons over here are in what we call are in pairs, right? That these are all pairs of electrons, whereas these 3 electrons over here are unshared pairs of electrons. A second thing to notice about this diagram in particular is the fact that as we're filling up, we go from 1s to 2s to 2p, 3s, 3p, but then we jump to 4s before 3d, and then 4p, and then 5s. And so for a lot of reasons that are much more complex than for us to get into today, the order in which our sublevel or subshells get filled up is not necessarily just in numerical order, that the process is much more complicated than that. I'm going to jump back to this just so you can see them without the arrows in there. There's a couple of different versions of the way that you could fill this up, or that you could write this in order to remember the order of this. One of them that I really enjoy, I'm sorry, I'm going to fill these in super quick for you, okay, would be to look at, or notice how this plays itself out in the periodic table, and understanding that our s orbitals are filled up over here, our p orbitals, our d orbitals, and then our f orbitals, especially if we remember that that fills in right over here. And so if I was looking at something like chlorine to write its electron configuration, excuse me, I would start from hydrogen, and I could just read from left to right and continue to fill in until I realized that the final part of chlorine is 3p5. But leading up to that, I have a 3s2, a 2p6, a 2s2, and a 1s2. But when I look at here's vanadium, what we just looked at, I could do a similar thing for any of my elements in the transition metals. I would read across 3p6, 4s2, 3d. So these four are all the D block, what we would call the D block, and they're depressed one. So the third is filled in right here. It's down one row. It's in the fourth row of the periodic table, but the 3Ds are filled in here, and that's consistent going down here. And then these guys, if they filled in right here, are depressed twice. So 6s, 4f, right? So we subtracted 2. So this is a handy picture, and it's a really nice kind of way that we can use the periodic table as a little bit of a cheat sheet to help us to understand how the electrons are filled in. This is one of those where you probably want to do a significant number of practice problems, and because we're running quick on time here, I'm going to move us forward towards our next topic. But go ahead and take a look at a lot of the examples that are available either in your textbook or through your teacher to be able to continue on with electron configurations there. Okay. Photoelectron spectroscopy is another way that we can analyze what's happening inside of an atom. And this is where we're going to have a very specific type of graph, we're looking at a model of how electrons, again, are organized within an atom. And we're trying to understand the relationship between the spectrum of an atom and its electron configuration, which we'll see in a minute, and the interaction between the electrons and the nucleus. So as we're looking at each of these, we should definitely make sure we answer the question that can see both of these things. Photoelectron spectroscopy is a specific graph that is going to have lots of peaks on it. And what we want to remember is that the position of the peak, and I'll give you an example of one of these here. Let's just pull one up. Okay, the position of the peak, we see this small little peak right here. Okay, the position of the peak is related to the energy required to remove an electron from that subshell. Okay, and so what we see is sort of a backwards scale, first of all, on our x-axis, right? So this is relatively close to 0 if the higher numbers are over here. What I sometimes like to think about is if this electron is if the nucleus were over here, let's say, and the electron is further away, it's probably easier to grab that electron and pull it away. So putting it over here helps us to understand that it's further away from the electron, which means less energy, right? And then the height of the peak is proportional to the number of electrons in that subshell. So what we're going to notice here is that this is right along our first line, which could indicate, since it's a relative number of electrons, here it's going to indicate that there's probably one electron that has this amount of energy. Let's call that, 1.5 or 1 3/4 of megajoules per mole in order to pull the electrons off of that sublevel. Since there's just one electron that is indicated here, we can assume that this is the photoelectron spectrum for hydrogen. And these are much easier to read, I think, once we start comparing them to other elements. So let's put up helium next to it. And there's two things that we notice. We notice that the peak went up to the second line. So we went to a second electron here, right? If this is one electron, then this one is two electrons. And the second thing that we notice is that the peak moved a little bit further away from zero. There's more energy that it takes to pull these electrons away. And we know that helium in its nucleus has two protons, whereas hydrogen only has one. So it makes sense that it would take more energy to pull electrons away from a helium nucleus than it would from a hydrogen nucleus. So two things I'm noticing here: the peak went up, and that the peak moved to the left slightly, meaning that there's more energy, or it's more difficult to pull electrons away. Let's keep going, and we'll compare helium to lithium. We notice that this peak of two electrons jumped even closer to, I'm sorry, moved further to the left, meaning that it takes more energy. Once we added a third proton in here into lithium, it's going to be even harder to pull these electrons away. But now we have a third electron out here. This one's going to be easier to pull away, in part because these two electrons are probably shielding it, and it's on a higher energy level, which corresponds to what we were looking at in topic 1.5. So we have this one electron that's right here versus the two electrons are right here. So this is going to be a little bit easier to grab. Lastly, let's compare that to beryllium. The same patterns are coming over and over again. We see that the peak slid slightly over to the left, and this one doubled. It's probably moved over a little bit to the left, but not too much here. We've got 4 electrons that we're showing here, and that's a key piece of information that helps us to see that this is beryllium. All right, so now why don't you give this one a try? Obviously, this is much more complicated. You notice that the numbers have shifted down here at the bottom. However, we still have the larger amount of energy is over here on the left. The smaller amount of energy is over here. If this is the complete spectrum that's given to you, can you tell me the electron configuration? And then ultimately what the identity of this element is? Pause for a second and see if you can do that. My solution to this would be to start from my left and indicate which part of the electron configuration I can correspond with each of these peaks. So here I see 1s2, 2s2, and 2p6. If I counted this out, 1, 2, 3, 4, 5, 6, all the way up here. Another 2 is right there. We're in the third principal energy level, and we're left with 3p3. I put all of that together. That tells me that this is the electron configuration for phosphorus. And if I were to add up all my electrons here, 2 plus 2, I've got 15 electrons, and that would be consistent with what's happening with phosphorus as well. Okay. There's lots of examples of these, again, on AP Central. This has appeared in a couple of different parts of the AP test. And so I would encourage you to keep looking for more examples like this. But writing your electron configuration across the top of the page, I think, is a really effective way for you to analyze this kind of a picture. Now, my favorite part of the lesson, looking at periodic trends, and what we are asked to do is to consider 4 different trends on the periodic table, 4 different properties of atoms that will change in a consistent way based on some behavior and some I guess I should say based on the organization of the atoms, and then their behavior the atoms will follow along with that. I always like to look at atomic and ionic radius first, because I think so many of the other trends will come from a clear understanding of what the size or the radius of an atom is. And so once we have an understanding of that, I think the other 3 fit in really nicely. So I'm going to start with atomic radius, okay? Oh, this idea, excuse me, that periodicity, right? That there are repetitive patterns on the periodic table, and that when we look at a column within the periodic table, we're gonna be able to make some really nice predictions about, if we know where something is, we can predict how it's gonna behave based on how the other atoms in that column will behave as well. So let's look at the radii. Okay, and atomic radius is just a measurement, generally in picometers, of the radius. So from the center of an atom to its furthest electron. Again, that's a way oversimplified example or model of what happens to an atom. We know that atoms are not actually spheres, but if we imagine them as a pool ball or a pool cue, a pool ball, we would see that if it has a larger radius, this is a larger sphere, versus a smaller radius, it would be a smaller sphere. Okay, I'm not saying that I think that atoms are spherical, but for this example and looking at radii, that's a really good model just for us to use in this case. So what we see as we read across the periodic table here, from lithium all the way over to fluorine, that we see that the radius is getting smaller, okay, from 145 to 50. We also know that as we go across, I'm labeling this as nuclear charge. Think about what these numbers could also represent as I go from left to right on the periodic table. What identity for lithium is a 3, beryllium is a 4, boron is a 5. If you said number of protons, then you're right. The nuclear charge, the charged particle in the nucleus, is the proton. And we know that there are more protons as we go across the periodic table, 9 protons over here. And so what that means is, even though I'm adding electrons as well, the size of the atom will decrease. I'm adding electrons to a second principal energy level. If these models look familiar, these Bohr models, they don't tell us exactly what an atom looks like, but they're a useful model in this example, or for this explanation, that I'm adding electrons to the second energy level. As I continue to add an electron, I go from 1 to 2 to 3 to 4 to 5 to 6 to 7 on that last ring. I'm also adding a proton to the nucleus, and because the effective nuclear charge, the pull that the nucleus has on those electrons increases, it's able to pull the whole radius in. And so as I look across a row on the periodic table, I would expect the radius to decrease because the effective nuclear charge, or the number of protons, is increasing, and they are pulling on electrons in the same energy level. Let's continue looking at fluorine here and look at what would happen if we go down the column that fluorine is in. Look at all of the halogens. We're going to notice that the nuclear charge is increasing again, right? From 9 to 7. These are some really big jumps as I go down the number of protons. And so I might expect that the radius is going to go down as well. That when I have 53 protons, that I would have a much smaller atom as well. But what I notice is that as I go down a column on the periodic table, that the atomic radius actually increases. And it increases because we're adding energy levels around the outside. Again, this Bohr model is a very limited model, but in this case, it works well because we're adding rings on the outside of the atom, because this iodine here has more rings on the outside. We would say that this is a larger atom, has a much bigger radius. Okay, so the nuclear charge increases as we go down the periodic table, but the number of energy levels for the electrons increases as well. And so that's an important piece of information that's going to give us a larger radius at the bottom of the periodic table. Here's a nice picture that kind of shows the entire periodic table, and it's pretty clear over here, our first group, that from hydrogen all the way down to francium. Francium would typically be considered one of the largest atoms on the periodic table. Okay, and we're typically going to have the smallest atoms over here. Hydrogen might be an exception just because it's only 1 proton and 1 electron, but these, certainly as we go across all of the other rows, we have smaller atomic radii. All right. If we look at ionic radius, so how does the radius of an atom change when we turn it into an ion? It's going to be a different story for cations and for anions. So for aluminum, and this would be typical for all cations are generally smaller than the atoms they came from. And why is that? Well, they lost electrons. And if we're clear, which electrons did they lose? They lost their valence electrons. So aluminum is maybe an extreme case because it lost 3 electrons, 3 valence electrons from its outer energy level. So that energy level is now effectively disappeared. But the number of protons on the inside of the nucleus stays the same. And because it has all of those protons pulling in on the fewer electrons that are there, what we could say is the effective nuclear charge is even greater. They're pulling those electrons in, and so the radius is pretty significantly smaller for a cation. For an anion, the explanation is just the opposite. We're adding electrons to an energy level that is admittedly probably already there, but the ratio of protons in the nucleus to electrons on the outside has now flipped towards more electrons on the outside. We have the same number of protons pulling on more electrons. They're not able to pull as effectively, and so the radius is going to get larger. And that would be consistent for most anions. Anions are generally larger, negatively charged particles are larger than the atom they came from. Cations are generally smaller. So if you were to look at these 5 sets of elements, these 5 sets of atoms, to see which one of them would have the same, which one of them has the same atomic radius, we would probably want to zero in on this group right here as being the closest to the same. We know that these are going to get much bigger as they go down. These are going to get much bigger as they go down. These go bigger and across. So even though they're going across, they're still going to be much bigger than one another. Okay, and these have even though they're similar to what's happening here, because these are closer to one another and we haven't jumped up a principal energy level here, we're going to say that this group, the group in black, has the most same atomic radius as everything else. I'm going to zoom through a couple of other trends, just being aware of what our time is right here. When we define ionization energy, we're saying ionization energy is the energy needed to remove an electron. So we're making something into a positively charged cation. Okay, and for me, again, I think this is strongly associated with atomic radius. If I understand atomic radius, this seems to make a lot of sense to me. If I have an atom with a small radius, or all of the atoms with smaller radii, it's really difficult to remove that electron, right? It's being held on to more tightly by the protons that are there. So our ionization energy is higher. And the opposite would be true for atoms with a larger radius. It's easier to remove electrons because meaning that the ionization energy is lower. It's easier to remove an electron that's further away from the nucleus. So the ionization energy is lower. We look at a graph or a version of the periodic table with ionization energies on it. And we see that all of these over at the right-hand side of the periodic table, which are our largest atoms, our smallest atoms have the largest ionization energy. So it's very difficult to pull an electron away from these small atoms over here. Electronegativity is defined as the ability of an atom to attract shared electrons. We see here that typically in electronegativity charts, we leave off the noble gases because they typically do not make a lot of covalent bonds. And so there's not a lot of shared electrons that they are going to be pulling electrons towards. I like to tell my students, E.T. Phone Home. That's probably a movie that dates me a little bit, but F, O, and N are 3 most electronegative elements. We've got chlorine right here. If we remember that these 3 or 4 elements over here are the most electronegative elements, that fluorine is typically considered the highest electronegativity value at 4, then everything else kind of decreases as we move further away from fluorine. And when we get into polarity of molecules, this is going to be a really important topic for us to remember. So we'll review this again when we get to that. Electron affinity is just the opposite. It's the energy change when an atom becomes negatively charged. And so we see we're going to have both positive and negative values here because they have energy is released here when we have electrons are, because fluorine is going to gain an electron very easily. It has a very easy place in its outer electron shell to add that last electron to make an eighth and a complete stable energy shell. And so this releases a ton of energy over here, whereas we'd have to force an electron to gain, or force strontium to gain it. We'd have to put energy in here. This is a calculated value. This is a theoretical idea, okay? So real quick, I'm going to zoom through these where we look at, if we considered the 5 elements that are circled here, which one do you think has the highest electronegativity value? We're going to look for the one that's closest to fluorine. So that's this one up here. Which one has the largest atomic radius? And that would be cesium down here in the bottom corner. Which one has the lowest first ionization energy? Well, we're going to look for the largest atomic radius because it's easiest to pull that electron away from something that is bigger. And so that's going to be cesium as well. And so you see, typically with problems like this, we're going to have the 2 opposite sides of the periodic table would be answers to questions we'd be looking at. Here's a great summary of all 4 of the trends from this topic, all put together on one screen. So this is a great one to take a screenshot of and maybe make a note of. Just remember that anytime you're asked to give an explanation of one of these elements or one of these trends, you want to talk about the chemistry, not talk about its location on the periodic table. So saying something like helium has the highest ionization energy because it's the top right of the periodic table would not be an acceptable explanation. But talking about its size, talking about its effective nuclear charge, its relationship with protons and electrons would be the best way for you to do that. Lastly, we're going to look really quickly at valence electrons and ionic compounds and understand that it's really important to understand how many electrons are on the outside of an atom, because that's going to help us to in our conversation of what's happening with chemical bonds, right? It's all in service to a good explanation of chemical bonds. And so we know that elements of the same column tend to form similar compounds, and that is because they have similar charges associated with them, okay? So I think we all probably have a version of a periodic table that has the number of valence electrons for each column in here. But if you don't have one of those already, here's just a really quick example of how the number of valence electrons as they go from left to right increases. 1, 2, 3, 4, 5, 6, 7, 8. Put them down here because I think you have a picture up on the top right of your screen. Didn't want that one to get covered up. And the number of valence electrons varies in here and is a little bit more complicated. And we'll leave for another conversation on another day. And then if we're looking at what the charges are that each of the columns in the periodic table make, we have a nice color-coded version here. I know my students have one of these in their notebooks already, where we know that metals on the left-hand side of the periodic table make positively charged atoms because they lose electrons at a predictable rate, 1, 2, and 3. And atoms on the right-hand side of the periodic table gain electrons at a predictable rate. These guys gain 1, 2, and 3. And the noble gases over here don't typically add or remove an electron, nor do anything in carbon's column. Okay, so I would imagine that this is review for many of the people listening to this, but just making sure that you have this in your brain when we're solving some problems that look like this. Atoms of magnesium combined with fluorine. Which other elements would you expect to combine with atoms of fluorine in the same ratio? And here we would go back. I'm going to go back just real quick, and I would want to say, notice that magnesium is here. So I'm going to look for any of the elements that are in the same row. So any of the alkaline earth metals would be great. A second problem that you might want to look at is, based on this information, we're going to look at hydrogen, lithium, sodium, and potassium. These are some oxides or some compounds that each of these elements make with oxygen. What would we expect rubidium to do? Noticing that as we go down this column in the periodic table, we're increasing the number of oxides that it makes. So we would expect rubidium to do the same thing and to behave most like potassium here, not like hydrogen, because it's below, because rubidium follows in right below here on the periodic table. Okay. So that was a lot of information in a really short amount of time, and I'm already over our allotted 45 minutes, our expected 45 minutes. So I apologize for that. I hope that you're still with us. I know that there's a lot that we shared with you today, but please go back and review, take some notes, take some screenshots so that you're feeling more confident in what we have there. I've got 2 exam practice problems for you to look at. Mr. Faribault will go over these with you tomorrow. This is from the 2015 free response question. We jump ahead to letter E, and I don't even remember which problem this is, but not important for you right now. You should be able to give me an electron configuration and then consider what sublevel the electrons would be removed from. And then the 2018, we've used that one a lot because it was lots of great information on that test. Question number 3. Right, the ground state electron configuration for an ion. So notice that this is an ion. And then when we look at the radius, use principles of atomic structure. Okay, so here's that phrase. We're not going to talk about where it is on the periodic table. We're going to talk about its atomic structure as evidence of why this behaves like this, why iron behaves like that. Okay. Just a quick reminder to keep going back to apcentral.collegeboard.org to get up-to-date information. We've got lots of extra resources at the bottom of the screen for you, and at that tiny URL. If you or anybody you know is still having trouble with the internet or getting a device on a consistent basis, we want to see your best work. So please either reach out to us directly or send your friends to this site so that they can get the resources that they need. Thanks so much for sticking with us today. I know we threw a lot at you, but it's always great to be with you, and we look forward to seeing you again in the next couple days. Have a great day.